Okay, in this section we're going to speak about SSL VPNs. So we're going to have a basic overview of what SSL VPNs are to begin with, what SSL is, what TLS is, then why do we need SSL VPNs, and then we're going to go, of course, go to the configuration side of both client-based SSL VPN and clientless-based SSL VPNs. So what is SSL? As the name states again, SSL stands for Secure Socket Layer, which means that it operates at the OC presentation layer where the socket is being opened. So the scope of SSL is to secure the OC socket layer. So what that means is that I want to have another way of protecting IP traffic, but not at the layer 3 level like IPsec is, which stands for IP security, but at the sockets layer. Now, SSL was created by Netscape in 1994, and the main first initial scope of SSL was to find a way to protect secure or secure web transactions. Now, current SSL uses version 3, which is defined in RFC 6101. Now, we have another variation of SSL which is called TLS. So let's see what TLS is. Where TLS stands for Transport Layer Security, which, as the name states, it operates at the TCP/IP transport layer where the socket is open from the TCP/IP point of view, and it's meant to secure the transport layer. So while the SSL was based on the, let's say, the naming was invented based on the OC layers, which was scoped to secure the sockets layer, TLS is based on the TCP/IP. Which means it is going to be what is aimed to protect the transport layer, because in TCP/IP layers above transport it's only the application layer. Now, why did we came up with TLS? So SSL had built-in design and security flaws which could not have been fixed based on how SSL was designed. If you want more information on that, you can go ahead and read on the RFC 7568. It's not a hard read, it's an easy read. It's a small RFC which just outlines a couple of the, let's say, problems, both security and flaws of SSL. That's why to fix the flaws, the IETF just chose to replace SSL, so no longer, let's say, do any kind of changes and any kind of new versions of SSL, but they had chosen to replace SSL with TLS. And of course, when TLS was invented, additional capabilities have been also added. So not only the flaws have been fixed, but also additional capabilities have been added to TLS. The initial version of TLS was version 1.0, defined in RFC 2246. Nowadays, the standard is TLS version 1.2, which is defined in RFC 5246. And of course, we have in draft TLS version 1.3. So why do we have all these versions of both SSL and TLS? Because clearly we had to add additional capabilities to the SSL TLS functionality, and also we had to fix, whatever to begin with was like another kind of flaw or another kind of something which didn't work properly, to call it that way. So what is the use case of SSL or TLS? Because we can nowadays, if you want to protect, let's say, the transport layer or the sockets layer, you can run either SSL or TLS. So both of them are still standards. Although, of course, from security point of view, it's recommended to use only TLS. Nowadays, SSL and TLS are used to secure not only HTTP traffic to be HTTPS, but also other application layer protocols. And the most commonly known ones are going to be SMTP Secure, which runs on TCP port 465, IMAP Secure on TCP port 993, POP3 Secure on TCP port 995, and FTP Secure on TCP port 990, and likewise LDAP Secure on TCP port 636. There are, of course, other protocols which make use of SSL or TLS, but those are the, let's say, most commonly known ones, where SMTP, IMAP, and POP3 are email-related protocols. FTP Secure, we know what FTP is, and LDAP is going to be the connection protocol which is used to speak with a let's say database, with an LDAP database. One of the use cases of LDAP being to speak with a Active Directory database scheme of let's say the Active Directory is nothing else but a scheme of objects like users, computers, and attributes of those users and computers. And of course, for the scope of our class, SSL and TLS is also used to secure VPN traffic. So instead of using IPsec, you may want to use SSL or TLS to fire up a secure VPN connection between two sites or between a remote access user and one site. Now let's see how does SSL and TLS work. So it's going to be something very similar from the fundamental point of view to IPsec. So just like IPsec, an SSL or TLS VPN, VPN or in general any SSL TLS session works in two phases. First phase is to negotiate the SSL or TLS tunnel, the control plane part. So end up with the secure keying material to protect the traffic afterwards. And then once negotiation had happened, the next step is going to be to actually transmit data over the SSL TLS tunnel, where data can be, as we saw before, FTP, IMAP, SMTP, POP3, LDAP, regular web traffic HTTP, which is going to be HTTPS, or for our use case is going to be a SSL or TLS VPN tunnel. Now both of those phases make use of what is called the SSL TLS vCore protocol. That's because if you think about it, like each of those protocols, LDAP or FTP or HTTP, were not designed to secure the traffic. Likewise, at layer 3, we don't have a dedicated protocol like built in the IP scheme to secure traffic. So between the layer 3, layer 4, between the layer 3 and layer 4 in the application layer, so if you want to secure a TCP session of type FTP or a TCP session of type LDAP or a TCP session of type SMTP, then we had to come up with something in between those layers to be able to actually bring in security. So that's being done through the vCore protocol, and both SSL and TLS make use of that protocol. Now, although SSL and TLS, of course, achieve the same thing in the end, allows to secure the IP traffic back and forward, because there are two distinct protocols, there are differences in the tunnel negotiation process. And of course, because TLS is the new standard recommended to use, TLS supports stronger security from both the control plane point of view, the tunnel negotiation, and the data plane point of view. But it's mostly from the control plane point of view that TLS supports stronger security. Now, the tunnel negotiation. So when we're going to speak about now about the control plane part. So in the tunnel negotiation process, what the two peers need to do is, first of all, they have to negotiate the SSL or TLS version, because based on that, different capabilities are being supported. They have to authenticate each other. They have to negotiate the key exchange algorithm, like it was in the case of IPsec, where the key exchange process was done through Diffie-Hellman asymmetric algorithm. In SSL or TLS, we have additional other capabilities in there. And also negotiate the cipher suite algorithms, like it was in the case of IPsec VPNs. So we're going to negotiate encryption algorithms, DES triple DES or hashing algorithms, just like in the case of IPsec VPNs. Now, tunnel negotiation always uses TCP, and the default port for TLS or SSL is going to be TCP port 443. Of course, that can be changed. And as I stated, based on the negotiated version of SSL or TLS, different capabilities are being supported. If you look on Wikipedia, in the transport layer security, as you can see in this table in here, based on the SSL version being used, let me use red. Based on the SSL version being used, or based on the TLS version being used, from the key negotiation point of view, which algorithms are going to be used to derive the keying material, different capabilities are being supported back and forward. Now, let's go step by step to those two processes of building up the tunnel, the control plane part. So in the authentication process, in the authentication part, this we have to do server authentication, so the server has to be authenticated. For example, if you look at our diagram, let's for the moment not speak about about VPNs, but just about a basic SSL TLS session. Like imagine test PCA would want to fire up a secure HTTP session to the web server of router 4. It's going to be an HTTPS session. So in this process, test PCA is going to be called the SSL or TLS client, or the TCP client, of course, because that's going to be a TCP session. And router 4 is going to be called the SSL or TLS server. And in most cases, the server has to be authenticated by the clients. And the server, in general, it is going to use a digital certificate to be authenticated by the clients. And the digital certificate can use RSA, DSA, or elliptic curve DSA as the algorithm, as you saw in this table in here on Wikipedia. Like for example, if we speak about, let's say, one of the algorithms like elliptic curve Diffie-Hellman RSA, as you can see, this is not supported by SSL version 2 or 3, but only by TLS version 1, 1.1, and 1.2, for example. And the server has to also authenticate the client. And the client can be authenticated by the server using, in general, the client is going to be authenticated as well, but that's not a requirement. But if the server is going to authenticate the client as well, then the client can get authenticated using single or multiple authentications. So the client can use also a digital certificate to get authenticated, or a username and password, or it can use both a digital certificate and username and password, or it can use a digital certificate and 2 sets of usernames and passwords. So clearly, top down, you're going to have stronger security. So ideally, you're going to have like digital certificate and username and password, or the third option where you use a certificate and 2 sets of usernames and passwords. Now, in the key management process, so just like in the case of IPsec VPNs, in the key management process, we exchange the algorithm which is going to be used to derive the keying material. So the secure keys which are going to be used back and forth on that session to secure the last messages of the tunnel negotiation, so the control plane, and of course to secure also the data plane, which is traffic being sent over the SSL or TLS session. So just like in the case of IPsec VPNs, in an SSL TLS session, after we negotiate, let's say, negotiate the SSL or TLS version, then we're going to negotiate the algorithm used to derive the keying material. And once the key material has been derived, then those secure keys are going to be used to secure the last messages of the control plane negotiation, and also afterwards, once the SSL TLS tunnel is being built, also the data plane, which is traffic being sent actively over that SSL TLS tunnel. And this is the same for, doesn't matter for for which scope you use SSL TLS. So it's the same process. Doesn't matter if you use SSL TLS to secure VPN traffic, or to secure FTP traffic, or SMTP traffic. It's the same process. And as you saw on Wikipedia, commonly used algorithms are going to be RSA, Diffie-Hellman, or ephemeral Diffie-Hellman, elliptic curve Diffie-Hellman, or elliptic curve Diffie-Hellman ephemeral. Just like as we saw in here on the Wikipedia section, based on which SSL or TLS version they negotiate, they have different capabilities, different options to negotiate for the key management algorithms. So how will the peers end up with the secure key material? What is the algorithm being used by both peers? Because of course they have to agree on the algorithm. Now the cipher suit, so it's going to be used to protect the data plane traffic. So we're going to negotiate integrity and hashing and encryption, which just like in the case of IPsec VPNs, integrity we have MD5, SHA-1 or SHA-2, But encryption, we have also RC4, for example, that's an option. IDEA, it's an option which is still used as a protocol, as an encryption algorithm. And of course, DES, triple DES, or AES. And of course, left to right is stronger. So RC4 would be the least secure protocol. IDEA is going to be more secure, and so on, with AES being clearly the strongest encryption algorithm. And like it, also for hashing, SHA-2 being the strongest integrity algorithm. So what happens is you're going to see in a couple of negotiation process, we negotiate the SSL TLS version, then we exchange some certificates back and forth, we negotiate the key management algorithm, then the security keys are being derived, and then the last messages of the control plane negotiation is being also secured, and then the user has to get authenticated by the server, and then the tunnel is being up and running, and then whatever is being sent over the tunnel is going to be protected. So also when the client gets authenticated, also the authentication part of the client, if it's like a username and password, has to be secure. Like imagine when you browse your Gmail account or any kind of webmail account which uses HTTPS, then when you put in there your username and password, those are already being secured, being securely sent to the SSL TLS tunnel. So the client authentication part, if it's not based on a certificate, the username and password from the client side to the server side are being sent over the securely negotiated SSL or TLS tunnel. So the data plane, once tunnel has been successfully built, all data will be protected as negotiated. So we're going to protect the data to the tunnel with a negotiated encryption algorithm, with a negotiated hashing algorithm, and of course we're going to secure that traffic with the negotiated keys from the negotiated key management algorithms. Now, data plane traffic being sent to the tunnel can use either TCP or UDP, where UDP encapsulation uses what they name to be DTLS or datagram TLS, which makes sense because it's called DTLS. It means that DTLS is supported only by TLS, not by SSL. The currently used version of DTLS is going to be version 1.2, and this is being defined in RFC 6347. Now, why would you want to send the data plane traffic over UDP, so by running DTLS instead of TCP, so through TLS? So looking back at our diagram, depending on, of course, of the use case, DTLS is not supported by all SSL or TLS sessions. DTLS is mainly used in VPNs. So what's going to happen when TestPCA is going to fire up a SSL or TLS VPN session with the VPN gateway, which is ASA3, is going to fire up an SSL or TLS VPN tunnel. Then what's going to happen is that in between the client PCA and the VPN gateway ASA3, we're going to end up, so the negotiation happens over TCP, and once we have negotiated the tunnel, and if we also negotiated DTLS, then between TestPCA and ASA3, we're going to have actually two tunnels. If TLS was negotiated between the client and the server, then DTLS can be used. If SSL was negotiated, DTLS cannot be used. So assuming we negotiated TLS, then what's going to happen is that from TestPCA to ASA3, we're going to have one bidirectional TLS tunnel, which runs over TCP, and one bidirectional DTLS tunnel, which runs over UDP. So then, based on that fact, why would we want TestPCA when it sends data securely to the SSL TLS tunnel to the VPN gateway? Why would the TestPCA choose to send data in the TLS tunnel or in the DTLS tunnel? And of course, the answer comes always if you understand what I said before, like TLS uses TCP while DTLS uses UDP. because UDP is a connectionless protocol and has less overhead, so the header is way smaller than the header of TCP, and traffic being sent for UDP session doesn't need acknowledgements, so it's a faster protocol. It means that we will need to run DTLS in a SSL VPN tunnel, because if we send any kind of real-time traffic to that tunnel, like for example a multicast stream, which is real-time multicast, or a video conference stream, video conference, or a phone call, so a voice call, voice conference, so whatever is real-time. For this reason, we invented DTLS, because if we have real-time traffic being sent through the SSL TLS tunnel, then we would want to send that data in the DTLS tunnel, not in the TLS tunnel, because it has less overhead and because it's connectionless. So in real-time applications, we don't want any retransmissions, right? So if a packet is lost, it's being lost, it is what it is. Like, you don't want, for example, imagine that you watch your favorite, football game, and that's, let's say, it's a real time, close to a real time stream, and you wouldn't want, like for example, if something happens at T0, like somebody makes a fault, and you didn't catch that because the packet was dropped, you wouldn't want to see that fault like 5 seconds later. That doesn't make sense. So real-time application is that if a packet was lost, it means that the communication is gonna be bad. You're gonna see that the stream is being blocked. It gets stuck. It no longer works. But you don't want retransmissions happening for real-time traffic. So that's one of the primary use cases of also negotiating DTLS, because we would want to send real-time traffic over DTLS, not over TLS. So we spoke about SSL and TLS. Before we go to the SSL VPN, so to see what is actually an SSL VPN now. So here in Wikipedia, you also see, so in this table in here, you have the key management algorithms, which can be negotiated between the client and the server based on which SSL or TLS version you run. And likewise, you have another table in here which states based on the SSL version being negotiated, or based on the TLS version being negotiated. Then likewise, they have different capabilities on the cipher algorithms, which are going to be negotiated to protect the last messages of the control plane and also the data plane traffic being sent over the tunnel. So for example, as you can see, AES GCM, it's only supported by TLS 1.2 and 1.3, for example, which is clearly going to be the stronger algorithm. While also AES by itself, it's only supported by TLS 1.2 or 1.3. So clearly, as I stated, based on the negotiated version of TLS or SSL, then you have additional capabilities to negotiate for the key management protocol and also for securing the data plane traffic back and forth. So clearly, it makes sense that ideally you would want to negotiate TLS and actually TLS version 1.2, so that the SSL peers or TLS peers, in this case, because they negotiate TLS version 1.2, so the TLS peers can actually run and use the stronger algorithms, so that both the control plane negotiation is more secure and the data plane traffic is being secured with stronger algorithms. And of course, you also have the hashing, which is supported. Like as you can see, for example, HMAC SHA-2 is supported likewise only by TLS 1.2. And of course, as you're going to see, both in a regular SSL or TLS session and in an SSL or TLS VPN tunnel negotiation, you can configure the server to allow only TLS version 1.2 connections, or to allow only TLS connections, or to also allow SSL connections. So of course you can configure, you can restrict that. You're not going to just let let's say the client and the server negotiate everything in there. Ideally, you're going to go on the server and say all incoming SSL or TLS sessions, I want them to be functional only if we negotiate TLS version 1.2 or TLS version 1.1, so no SSL being allowed in there. So what is an SSL VPN or TLS VPN? You can look at it like any other HTTPS session, but with a different scope. So of course the scope is going to be pretty much obvious. The scope being that if I want, this is a remote access user, for example, remote access user, and this is, for example, he's out on the internet connected, working from Starbucks, for example, and then on this side of the network it's the headquarters on this side. So what's in between in this area is going to be the transport network, which could be the internet or whatever else, doesn't matter. Usually it's going to be the internet if the user works from a Starbucks coffee shop. So then if I want that remote access user to be able to access resources from the headquarters side, it means we need to end up with a secure tunnel, so data is being securely transmitted through that VPN tunnel. So instead of running an IPsec VPN, we may choose to run a SSL VPN tunnel. So that's why we invented SSL VPNs. But of course you might say then, okay, if why do we need SSL VPNs if IPsec is good enough? So it doesn't mean that SSL is like stronger. It's a debate like which VPN tunnel provides stronger security, SSL tunnel or IPsec tunnel. In the end, you can imagine that because both IPsec VPNs and SSL VPNs support the same encryption and hashing algorithms in the end. And both SSL and TLS support pretty much the same, let's say, key management negotiation algorithms, not protocols, but algorithms. Then it depends like which one is stronger than the other. It all has to do with how strong is the key negotiation part, and how because in the end the data plane part is going to be clearly secured using the same algorithms, AES, triple DES or DES, and of course MD5 SHA-1 or SHA-2. So the main difference relies on how securely can the VPN gateways negotiate the key material using SSL or using IPsec VPNs. But of course, one of the main reasons or drivers of inventing SSL VPNs was because in some countries internet access is being restricted to allow only HTTP and HTTPS traffic, and of course also DNS, because without DNS web browsing doesn't work. So the problem is that in those countries, IKE, which is the key management framework used to negotiate the IPsec tunnel, and ESP or AH, which is the encapsulation of the packets being sent through the IPsec tunnel, that traffic is being filtered. So the user, if it's living or working temporarily in one of those countries, cannot fire up an IPsec tunnel back to the headquarters to send traffic securely in the network. So IPsec VPN is not going to work. Also, one other reason, because IPsec VPNs require a client to be installed, a VPN client to be installed on the end user side, on the remote access client. We may want to allow the users to fire up a secure VPN tunnel without the need to have a VPN client installed, like for example when working from an internet cafe. So as you're going to see, SSL VPNs allow you to fire up a VPN tunnel and send traffic securely back to in your company's network without the need to have a client installed. It's going to be called clientless SSL VPN. Now, most vendors, including Cisco, support only remote access SSL VPN for that reason, because usually you're going to have remote users which may temporarily live in those countries, and they need to be able to fire up a VPN tunnel back to the headquarters. But some vendors also have implemented SSL VPN for site-to-site VPNs. Cisco doesn't support that. And SSL VPN remote access has two variations. It can be either client-based, so you could still install a VPN client software on the remote access client. It's going to be the Cisco AnyConnect. or clientless, which means, as I said before, if the user works from an internet cafe, he's going to be able to still fire up a secure VPN tunnel to the headquarters by using just a browser. So in that point, it's going to be a regular HTTPS session from the browser to the VPN gateway, and I'm going to be able to access some data securely from the company's network. And Cisco supports both options, client-based and clientless-based, on both the IS routers and the ESA firewall. But the ESA firewall is more feature-rich, so in general, the ESA firewall is going to be a better VPN gateway from the features point of view as opposed to a regular iOS router. But both of them, both the IS routers and the ESA firewall, can act as a VPN gateway for both client-based SSL VPN sessions and clientless SSL VPN sessions. Now, before we finish up this topic, of course, based on the SSL or TLS version being run, and based on the scope of that, additional steps may be performed. But this is a simple overview, fundamental overview of the negotiation process, how this works. So we have on the left side in here the client, TLS or SSL, and on the right side the server. So if you run SSL or TLS, it may be there are going to be some differences back and forth, and of course based on the version you're running SSL or TLS, it means you support different algorithms, but fundamentally speaking, it's going to be pretty much the same process in there. So when the tunnel comes up, what happens is clearly, like the user fires up, let's say it's browsers, it's going to open up, let's say you're going to browse to your Gmail account or whatever, it's your webmail account. So the client's going to send in clear text a client hello message to the TLS server. And in that message, which is clear text, they negotiate. The client says, this is my supported TLS version, and this is my supported list of ciphers like encryption, hashing, and key management algorithms, and also optionally compression. The client says, hey, this is what I support, what about you? And then the server is going to, so the client is going to offer, let's say the client is going to offer SSL 3.0 and TLS 1.2. Based on the server's configuration, the server is going to choose, okay, so we're going to run over TLS 1.2 or over SSL 3.0. So then the server replies to the client, the second step, in clear text, and it's going to choose the TLS version, the ciphers algorithms, the compression method, and also the server, most importantly, sends its certificate. The server, in most cases, in 99.9% of the cases, is going to have a certificate. So the server sends its certificate to the client, which what a certificate means is, you remember from the PKI session, is nothing else but the server's public key. That's a certificate, the server's public key, the server's identity information, and then when the CA has issued a certificate to the server, is going to add in there additional data added by the CA, which is going to be like the serial number, validity dates, signature algorithm, additional data. And this message, this certificate is being signed by the CA's private key. That's the certificate. So the server sends back to the client, this is my identity, this is my certificate. And of course, what the client is going to do is going to, of course, initially validate the certificate. It has to be trusted. That's why when you browse to a server, an SSL sessions to a server that has a certificate which is not issued by a trusted CA, you're going to see an error in the browser saying this may be an insecurity. Do you want to continue? Then what the client does, and this is the next step, what the client does, the client selects a pre-master key. So client selects that randomly, and is going to send that master key to the server, encrypted using the server's public key. So the client knows the server's public key because it received the server certificate. And then what a server does, so this, what is yellow in here is going to be traffic being sent in clear text. So what is with yellow is going to be traffic being sent in clear text between the server and the client. This portion. This is clear text traffic being sent between server and client. And then whatever happens, whatever is being sent from this point on is going to be secured. So the client selects that pre-master key independently by itself, and it sends it to the server, and it encrypts that with the server's public key, which means only the server can decrypt that with its private key. Then also the client says change cipher spec finished, which this is an encrypted packet sent likewise from the client to the server, and that packet is being encrypted with the negotiated and derived keying material and with the negotiated cipher algorithms like hashing and integrity, hashing and encryption. Server decrypts the message using the previously exchanged keys, and then if the server successfully decrypts the message, it means the tunnel is being up. And then server says cipher spec finished as well. The server also encrypts a message to the client, so also the client can decrypt the message. So it's like the last two steps are like an acknowledgement between the server and the client, two-way. The client tells the server, hey, I'm done, and the server tells the client, hey, I'm done. And those messages are of course secured with the negotiated algorithms, hashing, encryption, and with the negotiated keying material. So at this point we can say that the TLS or SSL tunnel is up. The control plane part has been successfully negotiated.